So transition metals are the B group elements, and they fill their outermost shell, but they're also filling an inner d or f orbital. So this allows transition metals to move electrons between that d or f orbital that's being filled up and the actual outer energy level where they're filling up the s and the p orbitals. So that's why transition elements can transition or change the number of valence electrons. So transition metals have two valence electrons, but they can move one of those valence electrons into a d or f orbital so that they only have one valence electrons, or more often they move electrons out so they have 3 or 4 valence electrons. So valence electrons for transition metals generally vary from 1 to 5, depending upon if they move electrons or not. So to look at an example of this, copper is element number 27, and it's in period 4. So if we wrote the noble gas configuration for copper, it would be, I would use the noble gas argon, and that would take care of 18 of those 27. And then because it's in period 4, I would fill up the 4s2. And then if you look, now you go back and you fill up the 3d, and there are just 7 electrons left. So copper is 4s2, 3d7. And so it's got 2 valence electrons, but it's also got these 7d electrons, and it could move any of those d electrons out there to make it, anywhere from 1 to 5 valence electrons. It could also move one of these valence electrons into the d orbitals and have just 1 valence electron. So that gives you an idea of looking at the noble gas configuration, how you can take inner electrons, because the third energy level is not the outermost. So if you move any of these electrons from the third energy level out to the 4s, you may lose more than just 2 electrons. And again, looking at the example copper here, and just a reminder again, the inner transition elements are the ones placed below the main body of the table, because otherwise the table would have to be very wide, because they actually belong in rows 6 and 7. And the elements are filling the f orbitals when you're down in these inner transitions, so that's why it's 14 elements wide. And they're called the lanthanids and the actinids, and that's simply because they're by the lanthanum element and the actinum element. But again, they're very rare in the Earth, 0.01 or less for the lanthanids. And the actinids are all radioactive, so many of them have broken down into other substances by this point in Earth's history. So not a lot to really worry about with the inner transition elements, but when you see those 2 rows, that's why they're down there and not really a big deal for most of what we do.